Autoregressive large language models dictate modern AI performance, but their underlying architecture contains a severe physical limitation. The generation process is strictly serial. To predict the next word, the model must process the entire preceding context. Because step 2 cannot begin until step 1 is mathematically complete, text generation is locked into a one-by-one sequential loop. This serial loop creates a hardware bottleneck. The system spends nearly all its time moving massive amounts of data in and out of memory to calculate a single token, leaving the vast majority of the GPU's computational cores idle. This latency compounds in production environments. With the deployment of long chain-of-thought reasoning models that generate thousands of internal tokens before ever producing an answer, inference times now dominate the compute lifecycle. Throwing raw compute at the problem yields diminishing returns. You cannot accelerate a sequential bottleneck by simply adding parallel cores. To utilize modern GPU architecture efficiently, the inference pipeline requires a mechanism to parallelize text generation. The current industry approach to this bottleneck is speculative decoding. A smaller, much faster draft model is deployed to guess a sequence of future tokens ahead of the main pipeline. The massive target model then takes that drafted sequence and verifies all the predicted tokens simultaneously, executing in parallel what would have otherwise taken multiple sequential steps. However, leading frameworks like Eagle 3 contain a structural ceiling. The draft models they rely on are themselves autoregressive. Because the drafter still generates tokens one at a time, asking it to predict a longer sequence incurs an unavoidable compounding latency penalty. The longer the draft, the longer the wait. This linear scaling cost acts as a mathematical cap on the entire system. In practice, this limits the achievable inference speedup to roughly 3 times the baseline. Bypassing that ceiling requires abandoning the autoregressive drafting mechanism. This equation defines per-token latency. Drafting time equals the number of drafted tokens multiplied by the time per step. The cost grows linearly. To keep costs low, engineers must use extremely shallow draft models, which directly harms the accuracy of drafted tokens. DFlash restructures this pipeline by removing the autoregressive drafter. Instead, it deploys a lightweight block diffusion model. Block diffusion generates the entire sequence of drafted tokens simultaneously. It executes a single parallel forward pass rather than a sequential loop. Because drafting time is now decoupled from sequence length, DFlash can utilize deeper, significantly more expressive draft models without slowing down the system. This architectural shift flattens the latency curve, allowing for massive parallel drafting that operates at the speed of the hardware. Historically, applying diffusion to language models has been inefficient. Standalone diffusion models require multiple denoising steps, making them slow and prone to lower quality text output. If you force a small diffusion model to predict future tokens entirely on its own, it lacks the semantic depth for accurate predictions. The target model will reject almost every drafted token during verification. Previous attempts address this by using massive 7 billion parameter diffusion drafters. The sheer computational weight negated the parallel speedup gains. Therefore, for a highly efficient, small diffusion drafter to succeed, it must inherit the contextual intelligence already processed by the larger target model. Large autoregressive models implicitly encode trajectories for future tokens within their internal hidden states. The information needed to predict the next block of text already exists inside the target model. DFlash exploits this mechanism. When a prompt is submitted, the target model executes its standard prefill pass to generate the first token. DFlash actively extracts the hidden representations from 5 specific layers, sampled uniformly across the target model's architecture. These layers of raw information are instantly compressed through a projection filter, forming a dense data structure called the target context feature. This feature contains the task-specific semantic map required to guide the small diffusion drafter. DFlash isolates and exports the heavy reasoning of the target model, sparing the draft model from having to compute those semantic relationships from scratch. Getting that extracted intelligence into the draft model presents an engineering challenge. The traditional method, input fusion, injects the target features only once at the beginning of the pipeline. That early injection is structurally flawed. As the drafted tokens pass through the deeper layers of the model, the target's contextual guidance dilutes. DFlash handles extracted target features as persistent, immutable context. DFlash injects the target context feature directly into the key and value matrices of every single draft layer. This allows the masked draft tokens to update their query vectors while constantly checking back against the target context at every stage of the diffusion process. Because the contextual signal never decays, the token acceptance rate scales as you add depth to the draft model. Persistent KV injection couples the draft model directly to the target model's internal representations, creating a specialized diffusion adapter. This chart details benchmarks for DFlash on the Qwen 3 8B model. Compared to standard decoding, DFlash scales to a 6x speedup on Math 500. Evaluated against Eagle 3 on an identical budget, DFlash delivers a consistent advantage, reaching well beyond Eagle's peak. When an autoregressive system like Eagle 3 attempts to compete by increasing its draft tree size, it triggers a latency penalty during the verification stage. DFlash avoids this penalty. Its block generation latency produces higher acceptance rates while maintaining lower computational verification costs. The combination of parallel drafting and persistent key-value conditioning achieves a superior Pareto frontier of speed and accuracy. Moving from isolated benchmarks to real-world serving environments verifies the architecture's stability. When tested on SGLang hardware frameworks, the performance translates directly. Even under heavy production demands, scaling concurrency levels and varied batch sizes, DFlash reliably sustains throughput multipliers as high as 5x. Diffusion models function most effectively as specialized components rather than standalone generators. Text Diffusion's utility lies in acting as a fast, deeply conditioned parallel drafting engine integrated inside a larger system. By targeting the memory bottleneck and removing autoregressive drafting entirely, DFlash shatters the speculative decoding ceiling.